By the time you're in Algebra 2, and maybe even while you were in Algebra 1, you might have noticed that when we have a function of a certain amount of degrees, there is that amount of roots to that function. See, for example, we have a quadratic function. Didn't really care to write one down, but this is just an example of one. We have that parabola, and we see it crosses the x-axis on 2 points. And here we have a cubic term where the degree is 3. It crosses the x-axis at 3 terms. But what about functions, even functions, because if we have an odd function, it'll cross it eventually, right? An even function where it does not touch the x-axis at all. How can we find the roots of that function? Let's say, for example, we had just x squared, where it meets at 0, right? Because the 0 is the root, and we just move it up 1. Let's say our function was, f of x is equal to x squared plus 1. Now this function looks a little something like this, right? It does not touch the x-axis. But if we set this equal to 0, what happens? If 0 is equal to x squared plus 1, well, this is just a 2-step equation. Minus 1, minus 1. We have negative 1 is equal to x squared. And then from here, take the square root of that. And now we have x is equal to plus or minus the square root of negative 1. And now we see why there cannot be any real roots to this problem. The square root of any negative number is not a real number. The reason that is so is because square roots undo the squaring of something, meaning one number being multiplied by itself. Any number squared is going to be positive. A negative number multiplied by itself is positive. 2 positives, positive. So it is impossible for us to get a negative solution here. But here it is. How did we do that? Is there a way that we can describe, is there a way that we can use this non-real number so that we can describe polynomials that do not cross the x-axis and maybe even find out where they lie on a number line? Yes. The square root of negative 1 is known as an imaginary number. It is the first number you'll be introduced to that is not real. So we can just denote this as x is equal to I plus or minus I. There we go. When we have the square root, we get plus or minus on both sides. Because negative I squared, negative 1 plus I. Blah, blah, blah. That's why we have the plus or minus. So we still have 2 solutions. Here we get 2 roots, solutions. And here we still have those 2 solutions. They're just not crossing the x-axis. So now, let's see. I'm going to draw this line right here just to split up our work a little bit. Okay. Now, say we had a different function. Or let's not talk functions. Let's just talk equations now. Because I don't want to do all that, for 0. Let's just have separate equations. If we had x squared plus 3 is equal to 0, minus 3, x squared is equal to negative 3. Take the square root on both sides, and x is equal to plus minus root negative 3. And now what? Because this is not just 1, this isn't just I. Now recall, we can simplify the inside of roots. Negative 3 is the same thing as just 3 times negative 1. So we can have this radical right here be the square root of 3 times 1. Now, when we're adding within radicals, we can't split it up like that. But when we are multiplying, yes, we can. So this is just the square root of 3 times the square root of -1, which is just I. So x is equal to plus or minus root 3I. And there we have it. 2 solutions again. Let's try a different problem. Let's have x squared plus 9 this time equal to 0. Minus both sides, x squared is equal to -9. Let's take the square root, and like we did again, we're going to split it up to 9 and -1. So we have root 9 times root -1, and root 9 is just 3. So we have x is equal to plus or minus 3I. This is still an imaginary number. Well, it's not just I. We have this real number as we know it, 3. Recall, this is just I being multiplied by itself 3 times, right? 3I is just I plus I plus I, right? But can we add on real numbers to this? Let's try it and let's see what we get. Let's try a different equation. I'm going to move over here again. Let's do this time x plus 2 squared plus 4. And let's set that equal to 0 and then solve. So move over the 4, minus 4 minus 4. We get x plus 2 squared is equal to -4. And we're going to go ahead and square both sides, or square root both sides. Now, -4, like we did all these other times, we're going to split that up into 4 and then -1. So the square root of 4, 2, times the square root of -1, I. So square root of -4, 2I is equal, cancel, cancel, we get x plus 2, or plus or minus, almost forgot that. Plus or minus 2I, remember we have 2 solutions here. Now, take the 2 out on both sides, and then our solution, I'm going to move this over here. We have x is equal to 2, -2, plus or minus 2I. So really, I'm just going to expand this more, because this is 2 solutions. X is equal to -2 plus 2I, comma, to show that it's another set of solutions, -2 minus 2I. Now here we have a real number, -2, added and subtracted from an imaginary number. This is what we call a complex number. Complex number. That looks bad. We can do better. We can do better than that. Complex. Now, I on its own is also a complex number, right? This is just 0 plus I, right? Still complex. We have the real part and the imaginary part making up a complex number. So, obviously, how can we even put that on a number line, right? Because there are not real numbers, complex. How can we do that? Well, instead of trying to find a place to put it on a real number line, because a number line is the line of real numbers that you've known and played with since you were like a baby. This is not any part of that. We have to create a new number line, an extension of the real number line in order to plot these. So I'm just going to draw, I don't know why that's all there, just a number line right here. And this will be our real number line. I'm just going to call this real. This is our real number line with 0 as our center. And then it goes on. Now recall, 0 can also be seen as the center point of the imaginary number line, right? Because we're still increasing and decreasing by an amount of i's. As in the real number line, you go over 1, over 1, over 1, over 1. It's just on the imaginary number line, we are increasing by an amount of i's. So here, I'm just going to call this the complex. So in the real number line, you'll just have 1, 2, 3, 4, 5, 6, negative 1, negative 2, blah, blah, blah. But on the complex, this time, we will be increasing by an amount of i's. We go up 1, 1i, 2, 2i, 3, 3i, 4, 4i. And the same down. Negative I, negative 2i. I'm not used to writing it like an angle like this. 2i, and so on and so forth. So let's take this solution right here, plus or minus 3i, and let's try to plot that on this new number line. So 3i, we go up 3i, so there's 1, and then we'll go down another 1, and boom, there's our second solution. Pretty neat. But now what for this one? This one right here. We have negative 2 plus or minus 2i. So like with these, we're going to have two solutions, but now we are playing with real numbers as well. So let's just count down the number line like we did with real numbers and with this complex number line right here. So we're going to go backwards. Minus 1, minus 2, right? But this time we're going to go up and then down 2 imaginary spaces. It was up 1, up 2. There's our line, or our point, and then down 1, down 2. And there's our point. Complex numbers.